Okay, so I'm going to break down my distance measurement talk into two parts and talk for the first part about homonuclear distance measurement with fluorine NMR as the focus, but most of the methods that I show here can be applied to other spins. All right, distance measurement is something that is far more easily done in a solid state than in solution. So that's one thing that makes solid state NMR quite nice. And here's an outline of the different types of methods that are available to measure distances. I want to start with homonuclear distance techniques. And within homonuclear distance methods, I can distinguish two types. One is using isotropic spin exchange. And by that, I mean 2D correlation experiments. And I'm looking at signals with different isotropic chemical shifts. And I'm getting cross peaks, equivalent to NOESY in a solution state. And then I have a second type of homonuclear distance measurement involving anisotropic spin exchange. And by that, I mean, I'm looking at spins with the same isotropic peak. So if you do magic angle spinning, you get one peak. And yet I can still do distance measurement because I'm taking advantage of the fact that the same isotropic chemical shift, different molecules, you have different anisotropic chemical shift. So if you're neighboring tensors have different orientations, I can do a certain type of experiment to get distances. That's quite nice. And then I go into heteronuclear distance measurement. And I particularly would like to emphasize ReDOR as a really robust method. Jake Schaefer and Terry Goulian developed this, and my group has recently basically amplified ReDOR into multidimensional 2D concepts and applying it to fluorine spins. So I want to use fluorine to illustrate all of these distance measurement because that's our current interest, and a lot of people are interested in what you can do with fluorine NMR, taking advantage of the high gamma. And then I want to illustrate all of these techniques with examples to protein, membrane proteins and amyloid proteins. So a few early slides are about why fluorine is particularly useful as a distance probe. So let me first point you to this distance panel. This is kind of, if you remember in my basic lecture, I mentioned some examples of bond lengths, covalent bond. And of course, covalent bond length is not so interesting to measure. You want to go as far as you can to measure distances for spins that are not directly bonded. So I like to say, well, let's think about 30 Hertz dipolar coupling as roughly the lower bound of the coupling that you can measure. Anything weaker is demanding a very long relaxation time to sustain the magnetization, and it just gets very hard. If you use 30 Hertz dipolar coupling as the lower limit, and you say, I want to measure distances between carbon and nitrogen spins or carbon and carbon spins, then because of the gamma of these spins being pretty low, you really cannot see very far. For carbon-nitrogen, you can see up to about 4.7, 4.8 angstrom. For carbon-carbon, it's about 6.3 angstrom or so. And so that's all fine. They're useful still. But if your goal is to measure a few long-range constraints to help tie down the three-dimensional folds, then those low gamma spins won't do it for you. And this is why having a few high gamma spins could be really useful. And the gamma of fluorine is very high. Exclude tritium from consideration because tritium, although it's spin 1/2, it is radioactive. It's not a stable nucleus. So the highest gamma stable spin 1/2 nucleus is proton, and fluorine is 6% smaller in gamma. So on a 600 megahertz NMR machine, you have a 564 megahertz for fluorine Larmor frequency. So fluorine is pretty good for seeing far. So if you combine fluorine in a homonuclear distance measurement with 30 Hertz, you calculate this should be about 15 angstrom, should be possible. Of course, the detail is important, right? How do you measure homonuclear distances? Are you going to do dipolar recoupling, or are you going to just do spin exchange, spin diffusion? All these matter. And if you have relay transfer, of course, that changes what you think about the distance, how far you can go. But this is still a useful rule of thumb to think about what kind of distance you're probing. Why do we not talk about a proton spin in this context? We should. Proton fluorine is very good. If you have an otherwise deuterated system, so you reduce the proton density in your organic compound or in your protein, Because if you have too many protons around, it gets very complicated. You have line broadening due to proton-proton dipolar coupling still hanging around. But if you can budutyrate and you're doing that anyways for your system, then why not? Then you have just take advantage of the remaining exchangeable hydrogens, protons like amide, NH groups or OH groups. Then they're great as partners for coupling to fluorine. The reason I put this proton-proton coupling here as a nominal distance you can measure, but of course, with so many protons around, you'll never be talking about anything in a 1.5 nanometer range. You'll be stopped by the shorter proton-proton distances. Those will dipolar truncate the long distances. So this is practically not really meaningful. Okay, so fluorine is good because of its high gamma. Fluorine also is naturally abundant, so you don't have to label anything. There's no enrichment. It's already 100% enriched in nature. It doesn't exist in biomolecules in a natural way, but you can incorporate it in there. You can incorporate it in a very site-specific way so that you don't have to worry about detailed assignments. Usually you know which ones you have. Fluorine chemical shift is very sensitive to chemical environment and chemical structure, and that's very good. That means you can first resolve the isotropic chemical shift, and then in addition, you have anisotropic chemical shift. That's also useful. Although if you don't care about CSA, if you're not looking at motion and so on, that's something you have to think about when you do distance measurement, whether you have to overcome that CSA and how to overcome it. And the simple answer is spin faster. All right. Okay, we wrote a chemical review article with these curves. And what are these curves? This is dipolar coupling on the y-axis and internuclear distance as the x-axis. And different colors basically represent different combinations of the spins. And so that's just another way of showing these length bars. The proton-fluorine combination, which is shown in red, is this red line here. And this is the one that can still have a sizable dipolar coupling even when you go out to long-ish distances of 1.5 nanometer or so. And these other ones are just too hard to see. So this is a slide just to show that one can, without too much hard work, get your hands onto various fluorinated small molecules or medium-sized molecules or small proteins. You can buy fluorinated organic compounds, just simple organic compound or medicinal compound. You can buy these, and these things come usually with aromatic fluorines, as well as some aliphatic fluorines, such as CF3 groups. And we really like CF3 groups because their signal strength is very high, and the chemical shifts of CF3 groups are well resolved from aromatic fluorines, which tend to resonate between -100 ppm to -140. Medicinal compounds such as PET imaging agents come with fluorine because radiologists like to use fluorine-18 radioactive isotope to do PET imaging, and we just take the stable isotope version, fluorine-19, and there you go. So you can then start to think about questions like, where do these ligands bind in their protein substrate? Cholesterol is a membrane-bound molecule that can come in a fluorinated version. Sigma sells this. These things are not expensive to buy. And we can incorporate fluorinated amino acids into peptides or proteins. And if you do some peptide synthesis, you know it's pretty easy to put it in. If you don't do peptide synthesis and just want to express your protein, that's also fine. You just have to make sure the bacteria will take up only the fluorinated amino acid and not the typical hydrogenated amino acid. And for that, the simple way that my lab works on is to use glyphosate to stop the bacteria from doing its own aromatic amino acid synthesis from glucose, and rather it'll uptake the fluorinated amino acid you add. So no problem, this glyphosate-based method works quite well. So you can get fluorinated compounds easily. So now let's look at homonuclear 2D fluorine-based spin exchange experiment to get distances. In carbon-13 based solid-state NMR, people do that all the time. It's also in solution state. You basically get carbon-carbon cross peaks, and people read off intensities in approximate or qualitative way, strong, medium, weak, and so on. And that's the basis for then doing some structure calculation. So all of these experiments take advantage of spin exchange or spin diffusion, whether relayed or not, for chemically inequivalent sites. What I mean by that is basically chemical shift resolved spin exchange. And here I a few examples on small molecules, in this case PNC, and the underlying technique in solid-state NMR spin diffusion. No recoupling involved. You basically put your magnetization along the z-axis, then you wait for a certain amount of time, whether that waiting period is tens of milliseconds or hundreds of milliseconds if you want to get cross peaks for really remote spins. And then on the proton side, typically you would do something to encourage the X-spin spin exchange to happen. In the old days, when people don't spin very fast, you don't do anything on a proton. You don't decouple, because that way you can have the proton coupling to carbon or fluorine to help mediate spin diffusion. In the presence of proton coupling under magic angle spinning, your carbon-carbon spin diffusion or fluorine-fluorine spin diffusion actually happens a little bit faster compared to if you decouple. When you spin moderately fast, maybe 10 to 20 kilohertz range, then on the proton side, you would turn on the proton irradiation a little bit. That irradiation field matches the spinning speed. And this is the DAR condition, or also chord. So omega 1 on the proton side is equal to omega r in the simplest implementation. That's DAR experiment. And the reason that is helpful is when you do that, you kind of recouple proton coupling to carbon or fluorine a little bit. And what happens is then that the spin exchange between the two X spins, carbon-carbon or fluorine-fluorine, can become more efficient because of that broadening due to the proton coupling. That's the basic idea, and I'll show you the pulse sequence a little bit later. So here in this case, for a very sparse two-spin system, I have two fluorines on this small molecule, and I can get the free fluorine, all aromatic, 1, 2, 3. And I have 3 isotopic chemical shifts. The rest you're seeing are spinning sidebands. And I can choose the spinning speed, 15 kilohertz or 25 kilohertz. If I go a little faster, then the sidebands are spread out more, and the intensities that go to the sidebands are less. So I focus more intensities to the center band. So that gets me more sensitivity. Then I do this in a 2D fashion, fluorine-fluorine. And again, I focus more on the center band region, FO, FN, FP. And by waiting a certain amount of time, and I have 200 milliseconds here for spin diffusion to occur, I see a lot of cross peaks among these 3 fluorine sites, and that's all great. And then how do I get distances? Obviously, the shorter the distance, the higher the cross peak intensity, equivalent to nosy in solution state. What I do is then I follow the cross peak intensity as a function of mixing time for the fluorine. This spectrum is an example of 200 milliseconds. That's the longest I've done. I've also used much shorter mixing times in a 10 millisecond range, and I go and go. So you see what I'm plotting here is cross peak intensity as a function of mixing time. That's the growth or build-up curves. But I can also plot the decay time of the diagonal intensities. So this is the FP cross-section. I'm drawing a line here parallel to the omega-2 axis. And that diagonal peak intensity, of course, will decay, and the cross peaks will build up. And I can follow this for another site. And the idea is if the distances are short, then the buildup should be faster. So the buildup rate tells me something about the distance. So this being a small molecule, I know exactly what is the distance among these 3 fluorines. And the distance range is between about 4.7 angstrom to about almost 10 angstrom. And I can get the buildup rate constant. All of these, you see the buildup is single exponential. So I have time constants, something like between almost 20 milliseconds to about 70 milliseconds. I should tell you, well, this is nothing special. This is in a sense straightforward, but the time constant is pretty fast compared to carbon-carbon NMR. If you do a carbon version of 2D DAR, you would take much longer time, to see anything that is about 9 angstrom. You may not even see it within the T1 relaxation time. So this is what's nice about fluorine, because fluorine gamma is bigger, which makes the dipolar coupling stronger. All right, so I do the same thing for a different small molecule. This is sitagliptin, and it happens to be a medicinal compound, but the important thing to note is that this molecule is relatively long, and it has 3 aromatic fluorines all on one benzene ring, but then there's a CF3 group at the other end of the molecule, and the CF3 group has a very different isotopic shift of around -70 ppm. And these CF3 groups, even though they're far from all of these aromatic fluorines, they can establish cross peaks with these aromatic fluorines relatively easily. So distance is now up to about 10 angstrom, and the build-up rate constants, tau SD, is as short as about 7 milliseconds to about 40. So let me just look at the CF3 cross-section, again, drawing this line here. And I see cross peaks populated by about 150 milliseconds to all of these other three aromatic fluorines. And the build-up rate, the red one here, is about 12 milliseconds, and 10-ish, 19-ish, and then the diagonal intensities drop down in here, right? So I have a lot of build-up rate constants or build-up time constant, whatever you want. So here is the first time I show the pulse sequence. That's because I have space here. So this is the experiment that's involved, everything done, and the magic angle is spinning. What I do is I start from proton excitation, and then doing cross-polarization, CP, from proton to fluorine. This takes maybe about 100 microseconds, maybe a few hundred microseconds. I can dial how long I want it, depending on the spinning speed. And then I have fluorine chemical shift encoding and the proton decoupling. And then I store fluorine 90-degree pulse, and I wait for spin exchange to occur. And during that waiting period, I help things along by doing the proton. It's not really decoupling, it's recoupling, because I'm matching the irradiation with my spinning speed. So I broaden the single quantum profile of the fluorine, and I create a high overlap integral to promote, you can say, flip-flop term of the dipolar coupling. All right, and then I'm back to transverse plane by a second 90-degree pulse, and I have T2 detection. So that's the experiment. And here now I go to a model protein, GB1, where there are 3 tyrosines in this 56 residue protein, and distances are indicated here. And I basically fed the E. coli with glyphosate, and then I added natural abundance phenylalanine, natural abundance tryptophan, and then I added 3 fluorotyrosine. So phenylalanine and tryptophan don't show up at all. Tyrosine shows up, and the rest of the protein I could choose the carbon-13 label, or I don't have to. We usually choose carbon-13 label, so we can also take a look at the carbon-13 spectrum for some other purpose. But you can see basically in this 3 fluorine incorporated protein, I have a very sparse spin system, and I can measure these build-up curves. And again, I can then relate these build-up time constants with the distances that GB1 is supposed to have. It's structurally known. Okay, that's all good. And then we say, well, let's take a look at how this spin exchange rate is efficient or not. I would obviously have an interest to make that spin exchange go as fast as possible, so I don't have to wait a long mixing time to see strong cross peaks. And this is where you can try to optimize what happens on the proton side. And we basically showed that indeed, as we expected, doing a little bit of DAR or cord irradiation is better than not doing anything on the proton side. When you don't do anything on the proton side during this mixing time, then it's the experiment that solid state NMR people call proton-driven spin diffusion. That's the earliest version of proton-driven spin diffusion. It's still proton-driven because you're not decoupling. The fact that you're not putting out strong proton decoupling is already helping out things a little bit. But now if you recouple by doing a weak field, that's even better. So you can see that PDSD, these build-up curves, rise at much longer mixing times compared to cord. So PDSD is not as good as doing cord. So now the reason we took all of these model compounds that have well-defined distances and we measured the build-up rates or build-up time constant is that we want to see if it's possible to be semi-quantitative, if not quantitative, about the distances. Because you know, as I said, when we do carbon-13 NMR, nobody thinks about getting these build-up curves. You just say that takes too long, and I'm just going to look at strong, medium, weak cross-peak intensity. With fluorine, these 2D exchange experiments come relatively quickly, and it's not too much time taken to measure a few different mixing times. So I can do something that I think solution NMR people used to do, but no longer do, just to get the build-up trajectory, which we did. And so now with the build-up time constant that I told you about, tau SD, I can convert that to the inverse, the rate, KSD. And if you look into the theory of spin exchange or spin diffusion, loosely spin diffusion, I lump everything together, whether it's relayed or not. First, I just say, all right, it's spin exchange. And generally, the rate of that spin exchange is proportional to the dipolar coupling squared. So it's a second order effect. It's not proportional to the coupling itself, it's coupling squared. So there's an inverse R6 dependence, distance to the sixth power. But then the other quantity, which is very important, which for carbon-13 based experiment people don't do very often, is this F0 quantity. It's the so-called overlap integral that describes how efficient is it for two spins or two different isotropic chemical shift to actually exchange their energy or to have spin diffusion occur. And the idea is if there is some overlap, spectrally frequency overlap, the chemical shift is not too far apart, then this dipolar coupling or spin exchange can happen more easily. If their chemical shifts are very different and therefore the chemical shift difference is larger than the coupling, then it's going to be very hard for spin exchange to occur. And that overlap integral describes this concept. So this overlap integral is inversely related to the chemical shift difference between the two spins and inversely related in a square fashion. So if you have very large chemical shift difference, that shift difference will truncate the dipolar coupling that you really want to have in order to cause this transfer. With that understanding here, we can recast the buildup spin exchange, the buildup rate to be in this way. It's inversely related to distance to the sixth power, and it's inversely related to the chemical shift difference squared. So that's no problem. And then I can plot all of the KSD that I measured, which is the inverse of tau, time constant, in a logarithmic way as a function of distance. And if this fundamental understanding holds, then let me move the shift difference square to the left-hand side. So I have a log of the buildup rate times chemical shift difference squared. And then that should be related to log of the distance, but with a coefficient in the front of -6. So it should go down logarithmically. It should be a linear behavior. And that's indeed what we got for all of these small molecule or peptide or protein examples. We have y-axis KSD times delta and logarithmic. We have logarithmic here, and I get a slope of indeed -6. And in this logarithmic plot, if you ask, okay, is it -3, just dipolar coupling inverse instead of coupling squared, then it doesn't work. It's not -4 and so on. It's -6. That's good. You have a couple of outliers for some of these small molecules, and we can understand these outliers. And one outlier, particularly this one, comes from two cross peaks that have such small chemical shift difference. They're basically two peaks that are very close to each other. And for small chemical shift difference, you are in a strong coupling limit. So dipolar coupling strength is stronger than a shift difference. So that then works in a different way from what this equation will dictate. Okay, this outlier we can understand. And then I have a few points associated with CF3 groups, these trifluoromethyl groups coupled to these single CF bonds and so on. Those fall onto a higher trajectory in this logarithmic plot. And if you think about this, higher means, well, my intercept is higher. And that's nice. Higher means, well, the buildup rate is faster. I get to see the cross peaks at shorter time. That's great. I don't need to wait long mixing. Long mixing, you're always fighting relaxation. So CF3 groups are very efficient for polarization transfer compared to CF to CF. In addition to the fact that the CF3 group intensity is high to begin with, in addition to that, the underlying polarization transfer is just faster. So that's what comes out of these phenomenological, or what I call master curves or calibration curves for spin exchange involving fluorine. All right, so this is spin exchange by you just relying on the spin diffusion. You're not actively recoupling the homonuclear dipolar interaction. So that mechanism of spin exchange, if you were doing 100 kilohertz magic angle spinning using a 0.7 millimeter rotor, it gets very hard to do because the spinning is so fast, it'll quench any of these spin diffusion mechanism. When you're going faster, then we demonstrated these at maybe 25 kilohertz, 30 kilohertz, still works. You can use 1.9 millimeter rotors. But if you go faster, what can you do? So then you have to actively recouple the homonuclear dipolar coupling. So fluorine in this case. There are various homonuclear dipolar recoupling pulse sequences, and the usually simplest ones work easiest, even if the underlying efficiency may not be the ideal efficiency, but compared to fancier, more complicated pulse sequences where you lose a lot because of non-ideality, the simplest sequence usually still win out. And so here we use the RFDR pulse sequence, which basically involves a single 180-degree pulse per rotor period. So you say, I'm going now at 50 kilohertz spinning. My rotor period is inverse of that. It's 20 microseconds. It's pretty fast. And I'm just going to put a pi pulse in the middle of that 20 microsecond. And then the next rotor period, I do it again. I keep doing this. So that's my recoupling method. And this happens on the fluorine. And then the proton, you don't do anything. And so again, it's a T1, T2. I mean, otherwise, it's the same chemical shifting coding and then detection. Okay, so this works. And I can do it 25 kilohertz, moderate fast MAS. And you can see that the mixing time that you need to get cross peaks is an entirely different ballpark from the spin exchange. You're talking about a few milliseconds instead of waiting passively for 20 or 100 milliseconds. That's very good. This is what you kind of expect for active dipolar recoupling. All right, this is an example, 1.9 millisecond, again, sitagliptin, and again, even for the CF3 group, which is at the end of the molecule compared to the aromatic, they can establish cross peaks. So good. And now something on the order of 1 nanometer, I think this is like 9 angstrom to almost a nanometer. It takes roughly on the order of 5 milliseconds for you to see these cross peaks equilibrating to where they should be. Okay, so this is 0.3 millisecond is the build-up time constant for something which is 5.2 angstrom and 0.6 and so on. So very efficient. Also, the fact that the cross peaks have reached equilibrium can be seen based on the final intensities you're getting. What are we doing here? We're doing normalized intensity on the y-axis, and then x-axis is my mixing time. How do I normalize intensities? For each row, that total intensity should be 100%. And I'm following the fractional intensities. So if my 6 fluorine spins in the molecule, I have 3 CF3 fluorines, and I have 3 aromatic fluorines. If everything has absolutely exchanged magnetization and reached equilibrium, then everybody should get 1/6 of the magnetization. And that's indeed what I see here. This is basically about 16%. So that's pretty good. And I have that situation. So I demonstrate this fluorine RFDR on a peptide sample where I have a CF3 group on a methionine, and then I have an aromatic fluorine on a phenylalanine. This is methionine, phenylalanine, and leucine. Methionine, leucine, phenylalanine. Okay, so again, doing this is to try to get some time constants for the distances of interest. So what we find is that if you are having a small rotor anyway, and you can have the choice of spinning moderate or fast, almost 60 kilohertz, then generally faster is better because it keeps your total magnetization alive better, so you don't lose the magnetization as much. And so during the RFDR mixing time, so this is going out to about 15 milliseconds or so, and I'm tracking the total 2D intensity. I'm not just looking at individual cross peak. I literally just integrate the entire 2D spectrum. And you can see, based on just the visual impression, how as you go up to faster spinning, my spots are getting, okay, this depends on how you plot the contour, but nevertheless, I hope you can see that my overall intensities are doing better at faster spinning. And I'm putting out these RFDR pulse strings, right? 1 pi pulse per mixing time for them. So the mixing time here, I'm looking at somewhere around 2.5, 2.6 milliseconds. All of these are overall comparing similarly for these different spinning speeds. And I do better with overall intensity. So faster spinning is more efficient in preserving the intensity, and you lose less to relaxation mechanisms. All right, so with active dipolar recoupling by these pi pulses coming out, 1 pulse per rotor period, you have to start thinking about things like how the chemical shift tensor affects the dipolar recoupling. We looked into this, and this is something you have to do numerical simulations in order to understand, and it's a little bit complicated. We know that the aromatic fluorines have relatively large shift tensors, and you can go into the literature. These things have been measured. You have some idea which directions the principal axis point to. So that's one thing to think about. And then you also have the issue that even if you say, I want to just measure, let's say, the cross peak between this fluorine and that fluorine, FO and FP, that are close to each other on the same ring, I have some other fluorines hanging around. They're not too far. You have a FM here, and you even have a trifluoromethyl group there. And they can cause some kind of relayed transfer, or they can dipolar truncate the coupling that I'm trying to measure a little bit. So here in these numerical simulation, we try to address this. I can go through some of these details into considering this tensor orientation. Let's just consider FO to FP transfer. So this fluorine to that fluorine, and they belong to the same ring, right? Same phenolene ring. And I have conformal 1, where the FO-FP positions are in this way relative to the remote CF3. But if my phenolene ring flips, then I can have FO-FP in a, let's see, in conformal 2. So then the distance from the CF3 changes. Or if you think, all right, imagine that I don't have the CF3. It's not having any influence on what I'm doing on the phenolene ring side. Then I have that conformal 1 without CF3. And the numerical simulations are saying that basically conformal 1 to conformal 2, the red and the blue, are different. So depending on how far the CF3 is, based on whether my phenolene ring is flipping this way or that, I have a somewhat different polarization transfer profile. In other words, there's relay transfer going on. In one of these conformers, the relay is helping you to get the cross peak better. Then if I don't have CF3 groups, it's not doing any influence, then I have a different orange simulation, different profile. Although I must say the initial trajectories look the same, so that's good. Then in terms of tensor orientation, how does that affect your dipolar transfer? In the simulation, you can show, well, okay, if I pretend that FO CSA tensor, the orientation is changed by 90 degrees, and which one is changed? Well, if there are two tensors, I can always focus on the primary principal axis, the z-axis of each chemical shift tensor. And whether two tensors are this way or 90 degrees off, they're going to make a difference to the dipolar transfer. So this is the green versus the red simulation is trying to show that the tensor orientation changing the beta angle, which is one of the 3 Euler angles by 90 degrees, will affect things in a long time. So these simulations give us a sense of how the active dipolar recoupling is affected by CSA tensor. There's a moderate effect, but not too much. So perhaps a little bit more relevant is just how you're going to do the experiment if you're spinning that fast and you're looking at 50, 60 kilohertz, your rotor is turning around very quickly. And meanwhile, you say, I have to put a pi pulse in there. My pi pulse, depending on what's the RF field, if you're typical doing 50 kilohertz RF irradiation, that means your 360-degree pulse is 20 microseconds. So that pi pulse is 10 microseconds. So it's filling up half of my rotor period. So this gets pretty complicated. Normally, we think that our pulses are infinitely short delta function pulses. They happen instantaneously compared to any of your magic angle spinning. This is the old way when you don't spin all that fast and your pulse field, RF field is very strong. Now you're spinning very fast, your pulse is taking up a chunk of your rotation period. So how does this affect the mechanism of dipolar magnetization transfer? This set of simulations address that point. If you're going into the so-called delta pulse limit, and let's say I'm spinning at 25 kilohertz, and I'm putting out these pulses at a field strength of 83 kilohertz, then these two numbers mean that in my 40 microsecond of rotor period, my pi pulse is only 6 microseconds. So it's pretty good. It's short enough compared to the rotor period. Then I can imagine this is my delta pulse limit. And the spin dynamics for that is relatively well understood. We don't have to go into details. And what I'm showing here, the different curves, are different distances. orange is 5.4 angstrom. As I go this direction, I get to longer and longer 9 angstrom. So as you would expect, in general, long distance, the buildup would be slower, which is all good. That's what you expect. But what are the multiple curves within each color? There, I'm looking at how CSA tensor orientation affects things. I can pretend in my simulation, okay, the beta Euler angle is 0, 30, 60, 90. I just tried several different values. And you can see that the tensor orientation doesn't affect my mixing time dependent curves very much. And this is what I want, because if I actually measure a bunch of these polarization transfer buildup curves, I would like that to reflect distances instead of tensor orientation. So this works pretty well. Now, if I start to speed up my spinning and I'm using RF field that's not particularly strong, then this is what I call intermediate regime, where my pulse takes a fairly sizable chunk, 30% of the rotor period. Then the problem here is that my CSA has a significant influence on the buildup curve. So if I measure something in this regime, I don't know whether that's 5.4 angstrom belonging to the orange pack or whether that's 6 angstrom belonging to the black. So it's a little hard to say, right? You don't want to be in that intermediate regime. The best thing is if you go to the finite pulse regime, where you're spinning pretty fast and you don't do a hard pulse, you do a soft-ish pulse, even if it occupies 60% of your rotor period, because in this regime, the distance-dependent buildup curves are well separated. CSA tensor makes very little difference, and you can kind of intuitively understand that, because if you're spinning fast enough, you don't really care very much about the CSA. The anisotropy doesn't make all that much difference. And this is, remember, also the regime. Fast spinning is the regime where your overall magnetization, the overall intensity of the 2D spectrum gets much, much better than the slow spinning. So even though the delta pulse regime theoretically can allow you to separate distances, the intensities would just be very poor, and you don't want to stay in that regime. So this is a point that I want to emphasize, that the finite pulse version of RFDR, filling much of your rotor period with a pi pulse, actually works very well. And it's practical. It's just slightly fancier way of plotting, saying what I just said. If you consider MAS frequency and RF field strength, you would get the highest intensity in two regimes, either slow spinning and strong pulses, short pulses, or fast spinning and weak pulses. Okay, so I stop here and do codex then, so everybody can take a break.